All right, so part 5 of chapter 2. Something you have to remember about atoms is that cloud that surrounds them is an electron cloud. Electrons all have negative charges. So when we talk about getting these two things that are negative together to make any type of chemical reaction, you have to kind of take into consideration that there has to kind of be enough oomph behind that to get them to stick the way we want them to stick, to get them to have that chemical reaction and resist that repulsive force that they have. If you try and take the same side of a magnet and try to put them together, they kind of do this business because they don't like each other. Kind of the same concept. Now, what that ultimately means for atoms is you have to have enough kinetic energy to get them to hit with enough force to overcome that repulsive force from the electrons. That energy is actually called the activation energy. So activation energy is basically the bare minimum energy required for the reactants to begin a chemical reaction. Now, real life, the chances of those reactions happening fast enough to keep us alive are really, really slim. The best way I can think to describe it, imagine a nut and a bolt being put into a mayonnaise jar and shaking them and hoping that by shaking them, they actually spool together like they're supposed to. How long do you think that would take? Probably a really long time if I just put them both separately in a mayonnaise jar and went, how much energy would I expend doing this, trying to get them to spool together? That's the kind of random interaction we're talking about. Not only does it have to hit at the right time, the right orientation, but with enough force to actually get them to come together. So, how is it that we're alive? How is it that we actually still are here? There are these chemicals called catalysts, okay, down here at the bottom of the slide. Catalysts are like taking your fingers and taking the nut and taking the bolt and spooling them together to make them come together. How much energy did that take versus shaking the mayonnaise jar? A lot less. Yes, there's the requirement of having this thing that holds them in the right orientation and everything else, but it's still less energy than that random chance of shaking the mayonnaise jar. So, the catalyst is a substance that increases the rate of a chemical reaction without being changed or depleted. Okay? In other words, my fingers, when I do the spooling, did my fingers fall off? No. Did my fingers fuse with the nut and the bolt? No. Did my fingers, from this point on, they will never be able to put a nut and bolt together? No. So catalysts are kind of the same. They come, let's say these are the two substrates and I need them to come together. Okay. So I've got the two substrates. The catalyst comes in, puts them together, lets it go, and then looks for other things to put together. Okay. It increases how fast it happens, and itself doesn't get changed. It doesn't get depleted. It literally can go and find as many pin caps and pins and put them together over and over and over again. Okay. A catalyst is a chemical that can do that for us. And this is actually how our body continues to function. The chemical reactions in our body that keep our body alive and keep us going and give us the energy that we need so that we can breathe and our heart can beat and all of those are controlled by catalysts. Okay. So how can I change the rate of a chemical reaction? One thing I can do is I can change the temperature. As you increase the temperature, the reactants actually increase their kinetic energy. They increase how fast they're moving. Think about it for a second. If instead of taking the mayonnaise jar with the nut and bolt and doing this, I put it in a paint shaker that was doing this business really, really fast, the chances of them coming together are probably a little bit higher than me doing this with my hand. So when you increase the temperature, you increase that movement and they collide a lot more often, which means it increases the likelihood that you'll get them to hit with enough force that they actually stick. Okay? The other way is concentration. You can basically increase the amount that's there, which increases the rate of the reaction with an increase in the concentration of atoms that come into contact with each other. So let's go back to ball bearings. Okay, so we've got two ball bearings, one with a blue dot, one with a red dot, and I want the blue and the red dot to kiss. If I put one ball bearing with the blue dot, one ball bearing with the red dot in the mayonnaise jar, and I shake them together, there's a chance that they could do the whole kissy thing. But if I put 30 of the red dot and 30 of the blue dot together and shake them, the chance of that kiss happening actually went up. And I didn't change anything else. I didn't change how it was put together. I didn't put it into the paint shaker to make it move faster. It's just I increased the chances by having more of those molecules next to each other. So, inorganic chemistry. We're going to talk about water. We're going to talk about solution concentrations, acids and bases, oxygen, and CO2. So, real quick intro. Let's talk about the difference between inorganic and organic. Inorganic generally means that you don't have carbon in the substances you're talking about. Carbon is kind of unique in the fact that with carbon, you can make really huge, complex three-dimensional structures. So we talk about inorganic chemistry in chemistry as things that lack carbon and hydrogen bonds. There are three exceptions that have carbon in them, okay? And they're at the bottom there in orange. You've got carbon monoxide, carbon dioxide, and the bicarbonate ion, which is a buffer, which we'll talk about in a bit. When it comes to organic chemistry, though, organic chemistry is actually going to be the study of carbon-containing substances. Like I said, carbon is unique in the fact that you can build these huge, big, complex things with it. And you really don't see that with any of the other atoms in the periodic table. So the study of carbon-containing molecules is the study of these big, complex things. So looking at water, we already know this because we just discussed it, I think 2 videos ago. Water is polar. It actually does have a partial positive and a partial negative. The hydrogens are going to be that partial positive charge, and the oxygen is going to be that partial negative. That actually gives water by itself an interesting quality. Water sticks to itself. If you look down here, you can see water kind of forming this lattice work where you've got one water molecule binding to another water molecule. That lattice structure gives it a lot of stability. It means that it takes a lot to increase the temperature of water. It takes a lot to decrease the temperature of water. And to be honest, water is fairly stable because of that, okay? As far as percent body weight, 50% of a woman's body is water, 60% in men. Women have a higher fat content because we have breasts and we have hips because we give birth to babies. So that's really the only difference. But having that much water make up our body means that our temperature is actually fairly stable. It takes quite a bit of time for you to change the body temperature unless something internal is going on and your internal thermostat changes. Yeah, I can go outside and work for an hour. I'm not going to enjoy it, don't get me wrong, but I'm not going to go from being 98.6 degrees to 125 degrees because I went outside and worked for an hour. By the same token, if it's 40 degrees outside and I go outside and I spend an hour outside, my body isn't going to go down to 40 degrees in an hour. Okay? Something else, a large percentage, 92% of our blood's plasma, the stuff that our blood floats in, is actually water. We take advantage of the fact that water can dissolve things and things can dissolve in water because we use that to move things back and forth in our body. If we can dissolve sugar into our blood, then that can be used basically as a transport system to get that sugar where we need it in our body. So, there are 4 functions of water in living things. There are 4 functions of water in living things. There are 4 functions of water in living things. One of them I've already kind of discussed, stabilizing our body temperature. Water has something called a high specific heat, meaning it takes a lot of energy to raise its temperature. If you've ever made pasta, how long does it take for that water to boil? It's not like you put the fire to it and in 10 seconds, boom, you've got boiling water. It doesn't work that way. That means that it's stable. It's a stabilizing kind of thing. It's resistant to temperature changes. Water can also evaporate. And in our body, that's really important because when we sweat, the whole point of us sweating is that water in the sweat evaporates and takes the heat with it. At least that's the way it's supposed to work. We live in South Texas where, it's 100% humidity, so it doesn't always work that great. 2, protection. Water acts as a great lubricant inside of our body. So our organs are rubbing on each other all the time, every single second of every day. If you shift in your chair, if you sit, if you stand, your organs are rubbing. Now, imagine me taking my hands and doing this for 5 hours. What's going to happen eventually? Eventually, I would rub my hand raw, right? Well, this is with skin, which is designed to be fairly rough and tumble. And yet, every time I breathe and my organs shift around, they're rubbing. So how do I prevent them from rubbing each other raw? I put water in between the layers. And then I've got a lubricant that basically helps to make sure that they're slick enough that they don't rub each other raw, but more glide on each other. Think about a slip and slide, kind of like that. And imagine a slip and slide with no water and running and jumping on it. Yeah, exactly. So having that water creates that lubricant that allows that slipping and sliding with no damage. Something else that it does, it forms kind of a fluid cushion around certain organs. So for example, your brain is encased in your skull, right? Well, if it was just your brain and your skull and air in between, if you bump your head into a wall, your brain's going to hit smack dab on that skull, which isn't a good thing. So what we've done is we've put fluid around the brain, something called cerebrospinal fluid. And if you bump your head on the wall, and I'm not talking about going into a wall at 70 miles an hour or anything like that. I'm talking about, you kind of lose your balance, kind of punk. Your brain kind of does this business where it hits the fluid, but it doesn't get all the way to the actual bone inside your skull. Third function of water in living things, chemical reactions. We just talked about the hydrolysis reactions and the dehydration reactions, right? Being able to use water to break things apart or to put things together by taking water out. Those are chemical reactions. As well, using water to dissolve things. That is a huge part of something that, it's a huge function of water in our body that helps us to function better, helps us to survive. It's a mixing medium. So, what is a mixture? Let's define that first. A mixture is a combination of 2 or more substances that are blended together but not chemically combined. There is no sharing of electrons or losing or gaining of electrons. It's just mixed, okay? Tea is a good example of that. I can make tea, and technically I'm not doing chemistry in my kitchen. It's just that tea mixture is suspended or mixed in with the water. We have 3 types of mixtures. We've got solutions, we've got suspensions, and we've got colloids. So if you look down here in number 4, we've got solutions, we've got suspensions, and we've got colloids. So let's talk about those real quick. Or not, because you're not going. There we go. Okay. A solution. A solution is a mixture of liquids, gases, or solids in which the substances are uniformly distributed with no clear boundary between the substances. You've got two things. You've got the solute and you've got the solvent. Okay? So the solute dissolves the solvent dissolves the solute. Okay. Salt water dissolves in the solvent. Sorry. Salt water. If I were to define these, okay, the salt would be the solute because that's what is getting dissolved, right? The solvent would be the water because that's what's actually doing the dissolving. In a solution, let's say I make a glass of salt water. If I were to take a sample from here, here, and here in this glass, it would still be salt water. It's uniform. It's not like it's going to get saltier the higher I get or the lower I get. If I put a teaspoon of salt into, let's say, a gallon of water, I can take samples anywhere in that gallon container and it's still going to be salt water. Okay? We're not talking about like putting a cup of salt into, because that's like overflowing the system. We're just talking about an equal amount everywhere. That's a solution. A suspension is different. Suspension, let me read the definition, I'll explain. It's a mixture containing materials that separate unless they're continually physically blended together. In other words, the things that are suspended are so heavy that if you give it a little bit of time, they settle out of solution. The best example that I can think of is medicine. You go to the doctor and you get that liquid medicine that has clump at the bottom and liquid at the top. And when you're supposed to give it to yourself or your kid, you go to the fridge and you go, you take it, you put it back in the fridge, and within like 20 minutes, you got chunk at the bottom and liquid at the top. That's a suspension. The stuff that's there will stay suspended right after you mix it, but it doesn't take very long for it to actually fall out because it's suspended. It isn't in a solution. Then finally, you have the colloid. Again, let me read this and then I'll explain. It's a mixture in which a dispersed solute-like substance is distributed throughout a dispersing solvent-like substance. The dispersed particles are larger than simple molecules, but small enough that they don't immediately settle out of solution. So in your book, they talk about blood. And I just love that because, I've got a beaker of blood in my refrigerator right now so I can show you. No, I don't. I mean, come on. The best example I can think for colloid is milk. Now, I'm not telling you to open it. I'm not telling you to sniff it. I'm not telling you to do anything with it. Just go with me on the journey. If you take a half gallon of milk and you put it in the fridge, let's say I bought it today, it would stay milk for a good long while, right? Probably a couple weeks. Within that couple weeks, I could probably still have pretty good milk, right? But let's say that I completely forget that it's there and it gets put to the back of my fridge, and in 3 months I come back. Again, I'm not telling you to open it. I'm not telling you to sniff it. What's it going to look like? Don't tell me it's going to look like cottage cheese, because no. If you haven't moved it, if you haven't fiddled with it at all, there's going to be chunk at the bottom and kind of a yellowy liquid on top, okay? Milk is a colloid. The milk proteins that are in that solution are actually pretty heavy, but they stay suspended for a good chunk of time. If you leave it long enough, though, it will eventually settle out of solution. It's not as quick as the suspension. The suspension is 20 minutes and you're done. This is a couple weeks, 3 weeks, sometimes even longer. But the fact that you've got the ability to settle out of solution makes it a colloid. Okay, I hope that works. I hope that makes sense. So, solution concentrations. The concentration of solute particles dissolved in solvents. It can be expressed in several ways, but normally the most common way is to say grams per milliliter. So let's say I want a 10% sodium chloride solution. You would take 10 grams of sodium chloride and basically put it in a graduated cylinder and then fill that graduated cylinder to 100 mils. Now you're probably going, why the distinction? Think about it this way. If I fill a bathtub all the way to the rim of the tub and then I sit in it, what's going to happen? It's going to overflow, right? So my body takes up space in that bathtub. So in order for my body to fit in that bathtub with that water, I have to get rid of the water where my body is going to be. So when you're talking about making percentage solutions, you kind of have to take that into account too. Salt is a solid and it takes up space. So if you put it into a solution and you want to make a 10% solution, you have to take into account that 100 mils has to displace slightly to make room for that salt. So when you're making percent solutions, that's something that you have to think of. Acids and bases. So acids are proton donors, basically meaning that if you put this into a solution, okay, let's say hydrochloric acid, right? When it splits, it's going to become Cl minus and H plus. See that H plus? That's the proton donor. That's the hydrogen donor, okay? Acids, when you put them into solutions, split apart and release a hydrogen ion. If I am a base, I am a hydrogen acceptor, meaning that I will take this hydrogen into me, okay? The other kind of definition we have for a base is that it releases a hydroxide ion. So strongest base that I know of is sodium hydroxide, all right? If you put that into water, it releases Na plus and OH minus, okay? So it will become an OH donor. The thing is, if I have OH minus plus H plus, what does that give you? Water, H2O. I have two H's and an O, okay? There are kind of two families of acids and bases. You've got strong acids and bases. They'll either completely dissociate when they're put in water, will completely dissociate when you put them in water, and neither the twain shall meet again. In other words, if you put acid in water and it's a strong acid like hydrochloric acid, it's going to split apart and it's not going to come back together. FYI, don't do that in real life. It'll explode. Just letting you know. Same with a very strong base like sodium hydroxide. Again, this is not something that you do willy-nilly because it'll explode. It's actually something called an exothermic reaction, and it releases a ton of heat. So if you do this too quickly, it'll actually cause the beakers to break. So, strong acids and bases, you put them in solutions, they break apart, they don't come together. Weak acids and bases are a bit different because, let me move this up here, because they actually have reversible reactions. Remember our reversible reaction where everything was in balance, where it had to be equal on both sides. On one side of the equation, you will have a weak acid. So in this case, this is the weak acid. How do I know that? Because when I put it in solution, it donates that hydrogen ion right there. It lets go of it. But since it's a reversible reaction, I also have a weak base. So if it goes this way, that gets attached back to this. Now remember, bases are hydrogen ion acceptors, right? So technically, weak acids and bases are kind of complements of each other. And depending on the balance, they can actually kind of help to keep things stable because they want to be in equilibrium in this reversible reaction. All right, so pH. pH stands for potential hydrogen. So remember, hydrogen means it could. So how much hydrogen is there possibly? Potential hydrogen. It's basically a mathematical way to refer to hydrogen concentrations in a solution. By the way, that bracket, I don't remember if I've told you this, just means concentration. So if we look over here, this is the pH scale. Goes from 0 to 14. 0 being the most acidic, 14 being the most basic. Dead center in the middle is going to be neutral. Okay, so neutral. So water, if we have just pure water, that would be neutral because we have the same number of OH minuses as we have H pluses. So it's perfectly in balance. Anything below that, going towards 0, is going to be acidic. Anything above that, going toward 14, is going to be basic. So if we look at the acidic, urine is already at a 6. Vinegar is already at 3. Lemon juice is at 2. Stomach acid is at 1. Hydrochloric acid is at 0. It's the only other thing that I know of that's that acidic is sulfuric acid. So you go down, that becomes more and more acidic, the more H pluses you have. So as we go this direction, there's an increase in the number of H plus, okay, hydrogen ions. Now, as we go the other direction, as we go 7, 8, all the way to 14, that number of hydrogen ions gets smaller. So smaller number of hydrogen ions. Okay? Now, something I want you to keep in mind, because I think people think, oh, it's basic, it's safe. No, it's not. Depending on how basic something is, it can just as easily eat through your flesh. So at number 14, we have sodium hydroxide. Sodium hydroxide can melt your flesh off your bones. Literally can melt your flesh off your bones. If you've ever seen Fight Club, that thing that he burns his hand with when he's making soap, that's actually sodium hydroxide. Now, this is the interesting thing about bases, though. Bases have a tendency not to burn like acid does. So even though you may see it doing damage, it may not feel as bad as acid. So with bases, with really extreme bases, you almost have to be more careful because it doesn't necessarily click in your brain initially that something's wrong. Okay, so let's talk salts. We already talked about sodium chloride, right? It's a combination of a cation and an anion. The only exceptions are going to be H plus and OH minus because technically that's a positive and a negative, right? And normally they are formed by the interaction of an acid and a base. So if I took hydrochloric acid and sodium hydroxide and put them together, I would get water and I would get sodium chloride, table salt. Don't ever do that in real life. It's dangerous. Don't ever do that. Just FYI. But usually when we talk about creating salt, we talk about taking an acid and a base and putting them together. Normally not anything that extreme. It's usually a weak acid and a weak base. Now, buffers. Buffers are very, very important to us. The chemical behavior of a molecule can change as your pH does. One of the issues that we've got just in general with the function of our body, we've got a homeostatic pH. And if we get out of that homeostatic pH, things start going wrong really, really quickly. So our blood should be, I think it's 7.45 pH. Okay. I believe it's 0.005 variation before we start seeing really bad things happen. So, if an organism's ability depends on its ability to regulate its pH, how do we do that? Buffers. That's how we do that. Remember the weak acid, weak base I just talked about? A lot of the buffers in our body that help us maintain that 7.45 pH that we have are actually going to be that weak acid, weak base conjugate base pair. They're going to be the ones that help balance us out by either donating hydrogens or absorbing them. And having that balance means that we stay in our homeostatic window. So a solution of a conjugate acid-base pair in which the acid and the base components occur in similar concentrations. One of the, I guess, most well known for us is actually going to be the hydroxide ion, actually the bicarbonate ion. We use carbon dioxide to make one of the buffers in our blood. You know, the carbon dioxide that we breathe in oxygen, we breathe out carbon dioxide. Yeah, that carbon dioxide, we use it to make a huge amount of buffer. So there's that carbonic acid and the bicarbonate ion. This is the one that I told you guys we use carbon dioxide to make. Some others other than bicarbonate include phosphates, amino acids, and proteins as components. The greater the buffer concentration, the more resistant it is to the change in pH. But there's limit, okay? It works great for a while, but if you run out of buffer before you run out of pH change, you're going to be out of luck. So if you look down here, you can see that I've got quite a bit of acid, that H+. That's kind of the simplest acid on the planet. I've got quite a bit of that. If I keep adding acidic solution to this beaker, I'm going to get more and more of these, and my solution is going to get more and more acidic. However, if I've got a buffer is kind of like a sponge. These hydrogens that are just out here floating actually get bound to by the buffer. If they're not free floating out in solution, then they're not going to make anything acidic. So if this binds to this and this binds to this, there's no change in pH because the buffer basically acted like a sponge and took them out of there. So, oxygen. 21% of the Earth's atmosphere is going to be oxygen. It's essential to the life of most animals on the planet. Humans actually use it in the final step in a series of reactions in which energy is extracted from food. We don't need oxygen to breathe. We need oxygen to make fuel. And a big part of that is happening in our cells, in our mitochondria in our cells, actually. So oxygen isn't just needed to breathe, it's needed to make ATP. Carbon dioxide is actually a byproduct. It's a waste product of that metabolism that I was just talking about. Using oxygen to make ATP, one of the waste products is carbon dioxide. And we do have a small amount that is eliminated via exhalation. We get rid of carbon dioxide. But remember I told you about the bicarbonate ion and using it to make buffer. A lot of it is used for that. Now, just like everything, there's a homeostatic level. There's a balance. If we accumulate high amounts of carbon dioxide in our body, it's going to eventually become toxic and eventually it'll kill us.